Today let's continue with dynamic programming forever. So the first problem of today is go hole. We are managing a hole. They add end registration request to use a hole. Okay. Okay, so to simplify this, there is a segment from left to right, and there are many requests to use parts of the segment, and we need to find the most optimal way to be able to use the most of the segment. Okay, so let's turn on our whiteboard, and okay, so the segments cannot overlap. Okay, two requests cannot overlap. Okay, so for example, let's draw a segment here, and there are requests somewhere around here, kind of, and we need to find a way to maximize that. So to maximize the segments, okay, so let's visualize. So for every registration request, there's a left and a right value. So firstly we can sort the request by the left, and it should make grouping the request easier. Okay, so let's start with like our request here. 1 3 2 5. Okay, so let's divide our segment here to 1 2 3 4. So 1 and 3. The first one is 1 3. Second one is 2 5. Third is 4 6. Final is 6 and 8. So we must okay, so let's start with the first segment. If we so okay, for the first segment, then the longest is 1 2 3, which is 3 1 2 3. So the length is 3 1 2 3. The second segment 2 to 5. So we can either we take this and we find a we either take this or we done and use a segment before. So to take to 2 to 5 we have with a 4, and if since we cannot combine with the segment previously, the longest when we are at the 2 5 segment is a 4, so next is 4 and 6, 4. So we can either we take this and we find the maximum segment that ends before 4. So it is quite difficult for 6 and 1 3. So this the longest here is a 3 plus 3 is 6, 3 here and then 3 here. Okay, and then we have the segment that ends at 6. Okay, so we store the value here. So for the first segment, okay, actually let's sort it by right to left. Okay, so when we are at the third segment, we need to find the previous segment that 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 has the right most value less than our value. Okay, so less than the 4 here. So we do a binary search, I think. Okay, so we compute the segment up to okay, so I think I got this. So we have a DP right here, and DP I is the longest segment that ends at AI. So for DPI we can search the previous array that have the length satisfying the left segment here. We need to find all the value, the longest value until we get okay. So the idea is that we sort the sort the right, so the right edge, then build DP array. dp array equals to the longest segment that ends at ai. So in this dp build array, we iterate through each element, and so the dp I should be the high segment ai plus dp of previous segment that do not that doesn't overlap. And this is max. And we find this max value with binary search. Okay, we find the maximum value with binary search of the all previous segments. And okay, I think we have got the idea here. Let's build. Let's start with our code. First off, let me start my timer, and let's take the value here. Process the input data. Okay, now we have the longest array. We have the segment array. Nope. Vector. So we let's pay in first ai dot second. Okay, we have populated our array, so now let's sort the array by the non-capturing auto A and auto B return in wait nope return a second less than a dot second. Okay, we've got the sorted array. Okay, let's move it to the dedicated function. Max time vector request is the cons. No. We want to copy the array, so we use pass by value. So we sort the request. Okay. Return the max time of the A array. Okay. And now for first is a return in TP with length equal to request outside and TP 0 equal to request 0 minus request second. Okay, so let's define first no second minus request 0 first plus 1. Okay, and now for each equal to 1 and less than n plus plus. DPI will be we need to find the maximum and okay. We want to find the binary search here and equal 0 I minus 1 y less or equal than y. S prep equal to 0. Hold up. If we find the AI plus the longest, this wouldn't work. We need to ensure that hold up. No, not the longest segment that ends at AI. Should be the longest segment up to AI. Yep, this should be this. So we always have increasing sequence. Okay, longest segment up to AI. Yep. So it can be okay. As previous length equal to 0. So dpi be equal to base previous plus request I dot second. Okay. Yeah. Time of the request. We want to calculate the time of the request and in return dot second minus request plus 1. Request 0. Okay. Okay, so either we take the previous value that doesn't overlap with this request plus this request, oh, we just take the previous value I minus 1. Yeah. Request mid dot second greater than request I dot first overlapping then mid equal to left minus 1. Nope. Right equal to mid -1 else base previous equal to dp mid equal to mid +1 yep, and we have the dp alright, and so we return dp and -1, which is the highest value here, and test. Oops, is wrong. dp and -1 as previous plus tab this request. Okay, let's visualize 2 5 and 6 8 1 2 5 1 3 4 6 and 6 8 2 5 is 4 6 8 is 3, total is 7. Okay, so here our dp alright. Something not right here. Okay, so the base previous must be an array that request second. Okay, so I have sorted the array. Okay, let's debug. Second. Okay, we need to debug here. 3. Okay, so 1 3 we take it, and we have length of 3. Let's dry run it. 1 3 take it, it has length of 3 2 5. Well, we cannot take the previous, so it has length of 2 5 is 4 and 4 6. Okay, we cannot take the previous, so 4 6 is 3 plus the previous 3 equal to 6. Just for 6. previous okay, for 6 is 6 and 6 8 it is 3 here, and we can also always plus here. Alright. Okay, so now we need 2 DP array because we cannot. This one isn't the edge that end at 6. Oh wait, is it? For 6 is 1 3 and 4 6 and 6 8. Hold up. Only one, for example. Okay, I need to read the problem again. Any no two requests will have in them, the total usage time is maximized. Hey, wait a minute. 1 3 4 6 and 6 8. No overlap. Okay, I got it wrong. Okay, this one is greater or equal. Okay, so this should be our answer. The time. Okay, so I missed one case here. If for 6 and 6 8, and this isn't from 4 to before to before 6, but from 4 a.m. for example 4 a.m. to 6:59 a.m. so it won't work. Okay, so this should be our answer using dynamic programming and binary search. And let's try submitting the problem. Submit. Okay, accepted as expected. Yeah, we are doing well here. So let's submit now first. Okay, let me upload. Let me upload my answer for the first problem of the day. Create file. First solution. Okay, let me read the solutions here. Okay, this problem looks weird. No, this solution is, it looks elegant, but okay, it uses a approach that I haven't heard of. Okay. So instead of binary searching, he stores each okay, he store array of values that end at I. Okay, and we are, but okay, never mind. Let's go to the second problem. Knapsack. Okay, so there are n items. The item I has a weight W and the value V. Okay, so we need to choose a maximum value of items so that the total weight doesn't exist a given S. Okay, so let's use our robot again. So we have items. Okay, the item and the weight and the maximum weight. Okay, items that have weight and values. Let's one for one. So left is a weight and right is value, and 100. Okay, so we will want to store all the items. Okay. So for this I can store an array of weights up to the index I. And the current weight and the value maximum value. So like this we can take okay, so there are just 100 items. Then I do not need to use binary search here. just keep the maximum value and current weight uh, when taking the item. Okay, so let's use this as an example. So I got 1 2 3. The maximum weight when we take the first item, and it is only 4. Maximum value is 4, and current weight is 1. Next is 2, we have values 1. We can current weight it, we can take this with our current value, and we can have 5. Maximum value is we can no, if we ignore the first configuration, this should be current weight should be 1 plus 2 equal to 3. Next value is 104, but we cannot deduce of the old values. So we just how do we optimize this? Okay, so we need to optimize the weight. So let's start with the most naive approach. We either select an item or we do not. So by doing that, multiply with the number of items, we will have 2 to the power of n ways to select every item, each of the item. And okay, we need to simplify this. So with the previous okay, so there are 3 items. We either select the first item or we do not. And then we select it or we do not. We select the third item or we do not select the third item. So think we need to try otherwise. Not figure it out yet. Okay, so first let's sort the weight. One. Okay, we sort the weight and we have 1 4 2 100 and 4 1. Okay, sorting the weight looks better. If we select this, we have 1 and we have okay, so the right, let's say dp of 1 equal to 4 dp 2 we can no. So if we have weight of I don't want to try every possible ways, but okay, so 1 there is 4, 2 there is 100, 4 there is 1 1, and we for example there are more items here. Okay, so let's for example from the weight 1 here. Okay, so 0 0 0, there will be no value whatsoever. So here's the weight and here is the value. And now we start with 1. We have value of is difficult. Okay, so this is 01 knapsack. Okay, it's a bit difficult and I haven't come up with a solution here. So okay, I I feel that this is not the same as the previous problems that I saw. Also, it is dynamic programming. Maybe it I cannot take advantages of previous states. So okay, so okay, let's populate all the possible wait a minute. No. So if we populate we keep track of all the weights and the value here. So if we have weight of 0, it means we take nothing. Is 0, but at 1, and if we are at 1, we can take the 4. We take the item with the weights of 1 here, and we get a value 4. We can also get value of nope, and continue. If at 2 we have 100 here. And next we have okay, so let's populate this. For we have 1, 5. Okay, so this is the initial value, and we can nope, I don't know. Okay, let's use a more complex problem. Okay, so weight and value, so like 1, 1, 2, 2, 5, 5, 6, 7. This let's say random weights, random values. 5, 4, 8, 9, 2, 11, 15. Okay, and now we draw it on the table. So at the weight 1 we have 5 and 4. At 2 we have 9 and 2 and 5, 4, 5, 6, 7. Here we have 5, we have 2, value 2. Value. At 6 we have 11. At 7 we have 15. Okay, so with this information, what can we do? What can we do? Okay, let's put a constraint. So the maximum is 9, for example. And we need to build up the table. We can 5 of 4. How do we combine? Shit, I cannot even. How to know which one to not include in the bag? Okay, since we do not know that, we can only choose. Okay, so let's start from 1 here. We will have 1, we have 5, 4. If we go to if we add it, it will be 9, 9, 9, and 2. Okay, so the summation of these gives us 992, and now the summation of these we have 9 plus 9 equal to 18. We can have 18 here. Okay, this wouldn't work. to achieve 5 plus 4. Okay, so let's build up gradually. Okay, so at weight 1 we can find the maximum weight. Okay, so if it is here we have 5 as maximum, and then we go to 4, we have 9 as maximum, and next is 9. This 9 here can combine with the current 5 or 9 before. Okay, so we don't know the optimal way to put the item to the bag. So okay. I think the point of this is that we either put an item into the bag or we do not. So it will be okay. Like an explosion of states. Okay, so at here we can no. So is there 100 items and there are 2 to the 100, and we cannot calculate that. Okay, so we can encode all the possibilities and we okay, so let's for example we have n items, we have 5 items, and we can encode with assign an index for each of them, and we can encode them as 1, 2, 3, 4, 5, and we can say also 0. So when we are at the index 4, we must try all other combination, which is this will not end well. One, two, three. So there are like 6 combination. To combine with the fourth value, and they are all different configurations, so we cannot this is just redoing the 2 to the power 10 of n ways. It doesn't show anything. Any possibilities? I just suck at this. Okay, so we cannot exhaust all the possibilities. Maybe some possibilities. Well, I don't know. Maybe we should only care about a few possibilities and ignore all of the remaining. repeating the problem again. We can choose an arbitrary number of items as long as a weight do not exceed a given age. Okay, so they are like just 100 items. This shouldn't be. It shouldn't be this hard. Hmm. Oh, wow. 100 items, and we sort it. And what do we do next? Do we even need to sort the items? I don't know. Mhm. Okay, so like if we okay, so let's say for example we have exhausted all the possibility of the previous options, previous items, and we only add this one. No. Sometimes no. We still need to acquire. Okay, let's try it again. Maybe if we tabulate it as this way, is an index, and this is a weight, and we start with a 0, 1, 2, 3, and here is a value. This part of the quadrant here is the value. Index 1, 2, 3, 4, 6, 7. Okay. Can we build up the table here? Okay, so at index 1 we will have a weight of 1, 2, 3, 4, 5, 6, 7. We limit it at 9, 6, 7, 8, 9. Okay, there are 7, 1, 5, 6, 7, 8, 9. there are 9 items here, and at weight 1 we start with weight 1, index 1. We have value of 5. Okay, and that's all. And next is at the index 2 we can have weight of 1 plus 1. Okay, so either we use, okay, so this is a maximum value that we can get with this weight at index I. Okay, it does it might work here. Okay, so at index 2 we have a if we compare the previous weight with our current weight, then here at the value of 1 we can calculate 5. Okay, so 1 here is 1 plus 1 okay, this is 5, and the 2 here is 9. Yeah, next is 2, value of 2 here. We can add the current, three plus so let's correlate with the previous value 5, 9, and here it can be equal to 2. With the 1 here it will be a here is 2 at that value 2 here we can 2 here will be a if there's 2 then it can be 8. Or 8 or 9. This is 5, 0, and plus 8 equal to 15, 13. And we can also plus 9, which should be 9 plus 8 equal to 70. Okay, so next is maximum weight until this value. Before is 2. 1 plus 2 is 3. So we can calculate 5. It is 9. This one is 2. Okay, if its value is less than that, then we can calculate the max at the previous value. If it is equal, then we calculate the current. Compare with the current. Okay, so I think I have got it. Okay, so let's write our dp formula. Oops. dp I weight E and the index at the index I equal to dp so there are cases if AI less is the value of the weight of I is less than dp oh no let's name it this way. So if wi let's with the then dp I minus 1 w I minus 1 wi if equal to wi then dp and wi value by wi great. WI minus V minus we have the weight minus WI plus WI plus value I something not right here. Okay, so it might look like this. Yep, let's try it. Let's value of vector in okay. No, I don't think we need to sort, so we can use vector in for weight and okay, let's first take the n and s. With the n let's keep it for the simplicity. In items, find let's items first items second weight and value. And okay, let's create a table of value. Okay. So let's just keep the weight at maximum 10 to the 5. To the fifth. DP of plus 1. Of the same. Is fill with 0. Okay, then let's try out DP formula. So first up in DP DP 0 with new items 0 dot first equal to items 0 dot second, and now let's for each less than plus and for each weight assigned one is less or equal than s with plus. Okay, in the deep if we will consider if current weight and dot first current value items dot second. So the if current weight is less than is less than then it's a current which is less than W, then dp I and W equal to dp I minus 1 W else dp I W equal to dp I minus 1 W minus current weight plus I minus 1 W plus current value. Yep, this should be correct. And we return the result. So equal to max result and dpi w and we return the result. The in oops okay, what's this? Let's debug. Oops, this is wrong. Okay, we have n items. Oopsie. Let's print out the board. Debug it. Okay, so our array is full of garbage values. Something wrong with this. Debugging. Yeah, items array is correct. Items DPI oops, this should be like this. Yep. Yeah. One five. Okay. W lesson 104. This should be the correct answer. Yep, let's try submitting it. Okay, so we just need to represent the weights and the okay, should look like this. Our formula. Okay, let me try submitting. Oops, it's wrong. Why is wrong? Ah, okay. I forgot this. Okay, so if less or equal than s, and so you could okay, need to have this condition too. Okay, this is accepted. I think we can simplify our solution somewhere here, but I don't know. Okay, here first. Yep. Can we simplify it further? Okay. My motion tracker just got our answer here. This looks elegant enough. I hope so. Yeah, let me upload my second answer. Uh-huh. And yeah, we are done with 2 problems today. Wow. Took a lot of time for the second problem, but yeah, it is worth it. It's worth it. We found we get the table to calculate all the maximum value for each weight, and then we can copy from the previous weight, and tada, we have the optimal weight, optimal value for the design weight. And well, that's all for today. Thank you for watching.